Okay, so let's continue with our lesson on Lagrange interpolation. This time we'll be looking at interpolation mode P, where P is a prime number. And this is very crucial to us. Of course, the method of coming up with the Lagrange interpolation polynomial is just the same. Only that this time we'll be doing it mode P. We'll be reducing our calculations, all our calculations mode P, where P is a prime number. So that is the only difference. But the rest of our steps will remain the same. So the formula, again, is just the same formula. The only difference is we'll be doing mode P. So this is a summation of, this is Lagrange basis polynomial multiplied by its respective y coordinates. So that is, if you're given points, the following points, we will calculate the Lagrange basis polynomial for this point, then calculate for this point, then calculate up to the all the way up to p minus 1. Now, so after doing that, we'll multiply all those Lagrange basis polynomial by their respective y coordinates and then sum. So when you sum, what you get is the polynomial. And the way we calculate the Lagrange basis polynomial is the same way we did last time. And the formula is here. So if you're doing it with respect to the first coordinate here, then it will be x minus, you'll be getting, at that point, you'll be getting L naught of x. And this will be given by x minus x1 multiplied by x minus x2. So we omitted the point in question. We omitted that point in question. All multiplied by all the way up to x minus xn minus 1. Then divide by now the coordinate, the x coordinate of the point in question, minus x1 multiplied by x naught minus x2, and all the way up to x naught minus xn minus 1. Now you do that, every time you're doing this calculation, you reduce your result mod P. You can also just do without reducing, then reduce the final result. You will still get the same thing, but you'll be working with very huge numbers if you not be reducing along the way. So reducing along the way ensures that you then working with the small and manageable numbers. But as I said, you can as well work with those big numbers and then reduce later. Okay, let's look at an example, just how to do this. You've been given these points, and the question is compute the Lagrange interpolating polynomial mod 5. Mod 5. So the field, our field is this field of integers mod 5. So that's our field. Now these are 3 points. So that means our n becomes 2 in this case. Our n becomes 2 in this formula, because we are doing 3 points. So as we said, when you are doing this, if you are given 3 points, then we expect that your polynomial will be at most of degree 2. If you are given n points, then we expect that your polynomial will be at most of degree n minus 1. That is what we expect. Now, so the first thing as we've been doing is we now get the Lagrange basis polynomial for the L naught x, and that will be x minus the x value here, which is minus 2, and then x minus that, x minus 2, then out of x minus 2, No, not x, but 0. The x coordinate is 0 this time. 0, and then again 0, minus, just minus 2. Now, that is how I do it, and that is one way of doing it. The other way, you may want to change, you may want to convert this thing mod 5, this negative 2. Negative 2, you may want to convert it mod 5. When you do that, you get 3. So instead of having x minus minus 2, you could also have x minus 3. Get the same answer. You said you may want to reduce mod 5 at every step, or you may want to do it at the end of your working. So the way I'm doing it now, I've decided to do it at the end of the working. So that means I'm not reducing this mod 5. So this gives me x plus 2. And this other one gives me x minus 2. What about the denominator? It is 2. And then it is minus 2. So what do we get? The denominator will be negative 4. Now, this time I want to decide that I want to reduce negative 4 mod 5. That is 1. So I have x minus plus 2, then x minus 2. Negative 4 mod 5 is 1. So I said, it's you to decide what time do you want to reduce it mod 5. What time? There's no problem. You may reduce at one point, fail to reduce at another, but the final result must be reduced. The final result must be reduced. But in between, you may decide this time I want to reduce, this time I don't want to reduce. And depending on which one is convenient for you as you progress. But the final result, you reduce it. Let me take you through the working. Let me take you through the working here. Now, I had already explained up to this point. So I got that negative 4 mod 5 will be 1. So when you do that, this is what you get. This is what you get. So you may want to simplify this. You may want to open the bracket by just expanding. And when you do that, what do you get? You get x squared. No, this times that will be x squared. And then x times that will be negative 2x. Then 2 by that will be plus 2x. Then 2 by minus 2 will be negative 4. So the middle ones give you 0. So you arrive at this. You may want to maintain this negative 4 or reduce it, modify. Because this one is already positive here. So just leave it. But this one is negative. So you do it mod 5, just negative 4 plus 5, which is 1. So if you do that, that's where you arrive. Let me show you the other way that I'd already talked about, that you may want to tackle that point from the start. The point that was given to us was negative 2. This point is negative 4, 2. We said we can convert it to positive 3. So when you do that, then you would have negative x minus, yes, it's minus 3. Because negative 2, we've said is a congruent to positive 3. So this will be minus 3. Then this is x minus 2. So at the bottom here, we would have 0 minus 3, and then 0 minus 2. So when you do this, the numerator you get x squared, and then minus, this will be minus 2x, and this will be minus 3x, which becomes minus 5x. And then this x 3 and negative 2 will be positive 6. What about the denominator? The denominator will be negative 3 times negative 2, which is 6. So when you reduce this mod 5, the numerator becomes x squared plus 1, and the denominator is 1. So again, you arrive at the same thing. You arrive at the same thing. So I said, you choose when you want to reduce. But the most important thing is that your final answer must be reduced. Whatever you do in between, ensure that your final answer is reduced to mod P, where P is the prime number. In this case, our P was 5. Now, so then we proceed and get L1 of X, L1 basis, the Lagrange basis polynomial, L1X. So the point that we're considering, therefore, is this. So it means our L1 of X then becomes, our numerator will be X minus 0, then X minus 2 out of, this is negative 2. You can make it 3, because negative 2 mod 5 is 3. Then subtract 0 from this, and then also negative 2, subtract 2 from it. So the numerator becomes X into X minus 2, and the denominator becomes negative 2 multiplied by negative 4, which is what? The numerator is X squared minus 2X. Minus 2X, if you want, you can make it positive 3, mod 5. And the denominator is 8. But this is bigger than 5. Let's just reduce it. This will be X squared minus 2X out of 3. Now, this, we know what is happening here. What is happening here is something like this. Something like you have X squared, just a minute. You have X squared minus 2X. Then we are dividing by 3. We are dividing by 3. This is what is happening. This is what is happening. And we understand what happens. If this is the case, we understand what happens. What happens is supposed to be X squared minus 2X. Then you multiply by the reciprocal. Multiply by the reciprocal of these 3, which is 1 out of 3. So yes, you multiply by the inverse. This is the inverse of 3. This is the inverse of 3. So multiply by the inverse of 3. So this is what we have. This is what we have. And I've just tried to write it, what it means. What it means from the mathematics we've learned before in our primary and high school. It means we have X squared minus 2X divided by 3. So when you're dividing by 3, what follows is that you multiply by the reciprocal or the inverse of 3. So what this means, therefore, we are supposed to get the inverse of 3 mod 5. The inverse of 3 mod 5, which is 2. We know how to get that. It's 2. So it means instead of dividing by 3, what we then get is X squared minus 2X multiplied by 2. 2 is the same as the inverse of 3. So finally, we end up with 2X squared plus X. 2X squared plus X. You realize that 2 times negative 2 was negative 4X, but then I made it mod 5, reduced to mod 5. So that then gives us X. That gives us X. So you have 2X squared plus 1, 2X squared plus 1. And let's see, I think that's what I did. So it's just confirm so that we proceed. Yes. It's here, that's what I did, up to here, and you can see this 2, where this 2 is coming from. This 2 is coming from the inverse of 3, and I've explained how the inverse of 3 comes in. How the inverse of 3 comes in. So 2 here is the inverse of 3, so you arrive here, that is what we had obtained. So you found L1X. What then follows is to find L2x, L2x. And then after that, we'll be multiplying each one of them by the respective value of y. So let's find L2 of x. Okay, let me just create some space here. That we work close to our points. We see what is happening to our points instead of going far and then coming back. Okay. Now, so this time we're getting L2 of x, and we are considering the third point there. So that means L2 of x, therefore, becomes x minus 0, then x minus 2. Then 2 minus 0, then 2 minus 2. So the numerator then becomes x into x plus 2. And this one becomes 2 into, of course, this bracket, you're getting 4. So this gives us x squared plus 2x out of 3, because 8 mod 5. 8 mod 5 is 3. The same thing as before. This is the same as x squared plus 2x divided by 3, which means x squared plus 2x multiplied by 1 out of 3. 1 out of 3 is the inverse of 3. So the inverse of 3, therefore, mod 5 is 2. Is 2. So what we have, therefore, is 2 into x squared plus 2x. And this will be 2x squared. This is 4x. 2x squared, 4x. 2x squared, 4x. So that is what we have. I just want to confirm that we have the right workings also down there. So that if it's not the same, then it means I'll have to redo it, because these are the notes that we're supposed to we'll be having after the class. So I just want to confirm that it also agrees with what we've just done. So L2 of x, okay, it's the same thing. It's the same thing. This is what I got, the same thing. Only that at this point, I decided to divide this by 3 by 4 and wrote it that way. It's not necessary. We will just have worked with this, because when we work with this again, it means whichever we work with, at the end of our working, we'll have to reduce to mod 5. At the end of our working, we'll have to reduce to mod 5. Now, let's now check what were the corresponding values of y, so that we multiply by each of them. The corresponding values of y. X naught, no, L naught of x will be multiplied by 4. L1 of x will be multiplied by 1. L2 of x will be multiplied by 3. Those are the corresponding values of y. Good, so it's now easy. We just come here now, multiply L1 of x by 4, L naught of x by 4, L1 of x by 1, L2 of x by 3. Then the whole answer will be reduced to mod 5. So that's what is happening at this point. just multiplying everything by the corresponding y coordinates. The first bracket, what we are seeing there is 4x squared plus 4. The second bracket, what we are seeing here is 2x squared plus x. And then the third bracket, what you're seeing here is 6. And then minus 3. Collect like terms, this and that. That will be 6 mod 5. That gives us 2. Because 6 plus 6 is 12. 6 plus 6 is 12. This is 4 plus that is 6 plus that is 12. Mod 5, that gives us 2x squared. 2x squared. Now let's come to the excess of this. Then I have that. That's negative 2. Negative 2 mod 5. That would be 3. Because this plus that would be negative 2. Mod 5, that is 3x. What about the constants? I only have one constant, 4. This becomes the final answer. Because everything is mod 5. Everything is mod 5. That is the final answer you're seeing here. That is the final answer. Okay. I want to show one more example. Then after that, we go to the code and understand how the code works. Okay, good. I have 3 points. Again, is mod 5. We can even change it mod 7 or change it mod 9, mod 13 or mod 17. Where P is a prime number, we just want P to be a prime number. Because we know that in cryptography, then prime numbers will be very important to us. Doing it mod P, where P is a prime number, is very important. Otherwise, if you want, you can do it mod any other number. But now the problem is the inverses. The inverses. Now, you have seen that in some cases we've been able to look for the inverse. So if you're doing it mod any other number that is not prime, then some numbers would lack inverses. And when they lack inverses, then it becomes difficult for you to proceed when they lack inverses. Okay, let's look at this. We begin by getting L1 of X, L0 of X. L0 of X will be given by X minus 2 multiplied by X minus 3. Then the X coordinate of the point under consideration is 1. Subtract 2 from it. Then again 1, subtract 2 from it. No? Yes, we're subtracting 2, then subtracting 3. Subtracting 2, and then subtracting 3. The numerator becomes x squared. That is x squared. This is x squared. This will be negative 3x. And this will be negative 2x, which gives negative 5x. Then negative 2 by negative 3 will be positive 6. The denominator is negative 1 times negative 2, which is 2. Yes, because it's negative 1 multiplied by negative 2, which is 2. Now, at this point, so we are doing it mod 5. You may want to begin by reducing the numerator mod 5. There's no problem. You may want to begin by that. You may want to hold that a bit at some other stage. Let's hold it a bit. What does this mean? This means x squared minus 5x plus 6 divided by 2. Divided by 2, which we've agreed before, that will be the same as x squared minus 5x plus 6 multiplied by the inverse of 2. multiplied by the inverse of 2. Inverse of 2. But the inverse of 2 mod 5 is 6. I don't know whether there's somebody who doesn't know what we are doing together. No, it's 3. It's 3. I don't know whether there's somebody who doesn't know. We are using the extended Euclidean algorithm that so that if you have 5, you're dividing that by 2, and 2 goes there 2 times, and the remainder, of course, is 1. And this one is the GCD. So you make this one, which is the GCD, the subject of the formula. Make it the subject of the formula. This is the same as 5 minus 2 multiplied by 2. So then our question that we are answering here, the question we are answering here is, what is the inverse of 2? In other words, what element, when multiplied by 2, gives you 1? What element, when multiplied by 2, gives you 1? And you can see from this equation that the element that when multiplied by 2 gives you 1 is negative 2. Negative 2 mod 5 is 3. That's how we say that the inverse of 2 is 3. That is, I was just doing that for the sake of those who may have joined us after, because we had done these inverses earlier. We had done finding inverses earlier, inverses. Of course, there's an example that follows where you'll be calculating inverses. They're bigger, slightly bigger. The ones you cannot just see by naked eye. You have to calculate. Now, so let's proceed at this point. So we're multiplied by the inverse of 2, which is, we found is 3. So what we then have is that minus 5x plus 6 multiplied by 3. I said you may want to reduce mod 5, or you may want to do it later. Let's do it later. This will be 3x squared, negative 15x, then plus 18. Plus 18. Let's now do it. Reduce it mod 5. This is already mod 5. The remainder is 3. So that is 3x squared. This on division by 5, the remainder is 0. And 18 on division by 5, the remainder is 3. So this is what we get. 3x squared plus 3. When I was doing it, what did I get? Oh, something went outside the page there. Something went outside the page, but I did not simplify to the end. Oh no, it's not this, not this. It is the L naught of x is this. So I did not simplify to the end. I came up with this, but there's a 3 here. That means I did simplify towards the end. Towards the end. But as we said earlier, you may simplify even earlier, so that you just carry the answer down. But here I decided to simplify everything at the end. Now let's find L1 of x. L1 of x. So it will be, we pick the points. Pick the x values of the points not being considered. So we are considering this point 2, 0. This point 2, 0. So the other x values are the ones we use in the numerator. The other x values not under consideration are the ones we use in the numerator. But of course, we also use them in the denominator. So L1 of x then becomes, we are considering this point. So it will be x minus the other x values. X minus the other x values. Then the point under consideration, we take 2, the x-axis, the coordinate, the value of the x-axis, subtract 1 again, then to subtract 3 again. The numerator, we may just want to simplify. Minus 4x plus 3. When you simplify the numerator, that's what we get. The denominator will be 1 times minus 1, which is minus 1. There are several ways you may want to proceed with this. One may want to divide this minus 2, the numerator, and then reduce mod 5. The other person may want to change this mod 5 to get 4, and then multiply the numerator by the inverse of 4, mod 5. But I see that this is easy, just dividing the denominator into the numerator, because this is just negative 1. So this becomes then 4x squared, and this becomes 4x, and this becomes 2. What I did was, in fact, I got negative x squared, then got plus 4x, then got minus 3, and I just reduced the mod 5. So when you reduce this mod 5, this one, negative 1 becomes 4. And when you reduce negative 3 becomes 2. That's what I just did. Now, this is the final one, which we will then be carrying to the bottom. Let's see what we carried there. Yeah, of course, I had simplified it somewhere. Towards the end, I must have simplified somewhere. Right. I was simplifying them here. I was simplifying them somewhere here. Let us see where the other one has gone to. L2 of x. L2 of x. Now, so at your own time, you go through these workings slowly and slowly. See they are correct. You follow, see if you can follow them. Of course, writing the code, of course, we're using these steps. So you must know the steps. Then you can use them to write the code. Want to find L2 of x. The point under consideration is 3, 4. So we take x minus the other x values. Then we take the x coordinate of the point under consideration. Subtract the other x values. So again, this will be x minus 1, x minus 2. Out of this is 2 times that. We've already said that the inverse of 2 is 3. So the whole thing multiplied by 3. The whole thing multiplied by 3. So that is our simplified version. Now, after that, we've obtained the L0 of x, we've obtained the L1 of x, obtained L2 of x. We now multiply them by their corresponding y values and sum. Multiply them by their corresponding y values and then sum. You can see that x0 to be multiplied by L0 of x. L0 of x will be multiplied by 3. L1 of x would multiply by 0, but of course, then that becomes 0. Anything multiplied by 0 will be 0. Then this one multiplied by 4, the L2 of x. L2 of x will multiply by 4. So multiply by 3, 0, and then 4. 3, 0, and then 4. So this is why we are doing that. To get our polynomial, So multiply by 3, multiply by 0, then multiply by 4. Of course, this will become 0 when we multiply by 0. Now, you see, in our working, we had already simplified, but here I had not. So let me now simplify. This will be 9. Mod 5, it becomes 4. This will be 12. Mod 5 becomes 2. Of course, I maintained it, but at the bottom, I used the reduced ones, mod 9 mod 5, which is 4, and then 12 mod 5, which is 2. Then simplify to get the final polynomial. That's how you do it. That's how you do it. I'm sure this concept is now very clear, because it's not the first time we're interacting with it. So when you do that, this is the polynomial you get. This is the polynomial that you arrive at. Now, the following example, I decided to use slightly larger numbers just to give exercise of finding inverses and reducing mod 17. I'm now using mod 17 just to give exercise, just to ensure that those who have not done modular inverses can now use this to remind themselves how we're getting modular inverses. I will not do this example because we're just using the same steps. I can just point areas where I believe that those who are new can benefit a bit, especially the areas where I'm getting inverses. Like for instance, at this point I have negative 10. It's in the denominator, negative 10. I do it mod 17, that gives us 7. That gives us 7. So that finally what we have is x minus 5, x minus 12 over 7. That's what we have. Because negative 10 mod 17, just add negative 10 plus 17, you get 7. And we've already said that this is the same as x minus 5. Let me just write it here. X minus 5 is the same as that, x minus 12. And of course, this 12, if you want, negative 12, but let's reduce them later. This is the same as divided by 7. The same as divided by 7, which of course will be the same as x minus 5, x minus 12, times the inverse of 7. Times the inverse of 7. So I wanted to use this maybe just to remind those who are new how to find the inverse of 7. Mod 17. Using the Euclidean algorithm, we ask ourselves how many times does 7 go into 17? Because they're twice. Because of 14, and the remainder will be 3. Then we ask ourselves how many times does 3 go into 7? How many times does 3 go into 7? 3 goes into 7 twice. And the remainder is what? 1. So 1 is the GCD, therefore, of 17 and 7. 17 and 7. Those are the two numbers we're considering. We're considering 7 and 17. So the GCD, therefore, is 1. So now make this one the subject of the formula. So 1 becomes 7 minus 3 multiplied by 2. When you use the bottom equation, the equation at the bottom, what does this become? This is 7 this 7, 7, then minus, instead of 3, substitute the equivalent of 3. The equivalent of 3 is this. The equivalent of 3 is 17 minus 7 multiplied by 2. Then remember this 2 outside the bracket. Remember that 2 outside the bracket. So what do you come up with? What do you come up with? There is this 7, yes. And then just multiply this 2 inside this bracket. Remember there's a minus outside also. So we have something like minus 2, which we are now multiplying inside the bracket. And when you do that, you have negative 17 multiplied by that 2. And then again, that negative 2 multiplied by this. You have positive 7 multiplied by 4. Collect like terms. When you collect like terms, what do we have? We have a negative 17 multiplied by 2. And then this and that will be 7 multiplied by 5. 7 multiplied by 5. So the question is, we are getting the inverse of 7 mod 17. So in other words, we are getting a number which when multiplied by 7 would give us 1. And that number is 5. So the 5 is the inverse of 7 therefore. So instead of multiplying by 1 out of 7, we then multiply by 5. Because that is the inverse of 7. That's why you see the 5 here. That's how you see this 5. And that's why you see I said that the inverse of 7, the multiplicative inverse of 7 in Z mod 17 is 5. So that is how I got this inverse. I know majority of you are aware of how to get these inverses, but for the sake of the new ones, you can always do this. You can always revisit so that they can also know how we get the inverses. That when on their own they're revising, they can know where the 5 came from. So that is the point I wanted just to clarify. Because you cannot divide by a number like 7, that equation, you cannot divide, you cannot do that. It's better multiply by the inverse. Now look at this, look at this. Look at this. After simplifying, I arrived at this point. But look at the denominator, mod 17 is 1. That's why I write this. So it means the same as x minus 10 multiplied by x minus 2 divided by 1. So you arrive at that. So that is how it simplifies to that. Because the denominator becomes 1. The denominator becomes 1. What about this one? The denominator is 14. So again, we try and find the inverse of 14. When I did, I found 11. Inverse of 14 mod 17. Of course, you just be doing the same thing you've been doing. You're asking yourself 14 into 17, how many times? And what is the remainder? What is the remainder? And then what about this remainder into 14? What about this remainder into 14? This remainder going there 4 times. And the remainder will be 2. So what about this remainder into 3? What about this remainder into 3? Going there once, and the remainder will be 1. So you make this one the subject of the formula and replace the remainders as you go up. Replace the remainders as you go up. That's how you do it. If somebody has a question, maybe you can ask, and then we look at it. somebody has a question how to do that. Good. After getting L1, L2, and L0 of X, multiply them by their corresponding values of Y, and their corresponding values of Y are here. The corresponding values of Y are 14, 14, and then 13. 14, 14, then 13. That one I was doing it at this point. I was doing them at this point here. Where is that? The first one, multiplied by 14. Of course, when you do this point, this is 70. 70 reduced to mod 17 is 2. So instead of multiplying by 14 times 5, just multiply by 2. That's what you see here. I multiply by 2, then simplify, simplify, it comes to this. This one becomes 0. This one becomes 0. Negative 34 mod 17. 17 goes there negative 2 times. The remainder is 0. Now for this L2, L1x, this is what I expanded. Then I come to this. When you expand, you arrive at that. Then L2 of x, 13 times 14, I get 143, and reduce mod 17 to get 7. So instead of multiplying by this, this one is 7. This part here is 7. So you multiply that equation by 7. So when you do that, you arrive at this, and then reduce it mod 17 to give you the final result. Then bring those results together, just sum them. You collect like terms. Sum them and collect like terms. You come up with this polynomial as your final result. The following Rust program implements the Lagrange interpolation in finite fields using modular arithmetic. So if you are given a set of points, this program will compute the polynomial for you. The polynomial that will be passing through all those points. Let's just go through the program and see. I'm doing with the I64, that is 64, these are bits, 64 bits. I, as we've always said, is telling us that you can deal with both negative and positive numbers. So you let T, be mutable. Now in my code, R stands for the remainder, T stands for the inverse. T stands for the inverse. So what I want is, I want to get the inverse of a number. So if I want to get the inverse of a number, modular inverse, I'm saying that then let that inverse be 0. And let it be mutable. Then the new inverse, because this is mutable, it means it will be changing. So when it changes, you get a new inverse. Then it changes and you get another new inverse until you have the final inverse. The new inverse, you make it mutable and you initialize it to 1. What about the remainder? Initialize it to M. What is M? M is the size of the group. So for instance, if you are talking of ZM, so M is the size of that group. Then let the new remainder be A. So A, of course, is the number whose inverse you want to obtain. the number whose inverse you want to obtain. Let me show you, therefore, how we'll be getting the inverse. It says, while the new remainder is not equal to 0, while the new remainder is not equal to 0, you enter a loop. When you enter that loop, you let the quotient be the remainder divided by the new remainder. Then you let the inverse be temporary. You let the inverse be temporary and you let it be t. The inverse will be temporary and will be t. Then after you've made it temporary, now calculate the new inverse. The new inverse or t becomes the new inverse. Then what about the new t? Would be, how do you calculate this new t? How do you calculate this new t? New t is calculated by the temporary t, the one you made it temporary, then subtract this quotient multiplied by new t. That's how you do that. I'll show an example how to do that. I'll show an example with these steps. Then you let the remainder be temporary, just as we had done before. The remainder be temporary, and if it's temporary, and you initialize that it's r, of course we had done initialization at this point. Calculate new r as temporary r, the temporary r minus quotient multiplied by r, new r. When I show you the steps, I think steps will make this working clear. But that is how the code is. That is how the code is doing to get inverse. So this process continues until the new r is 0. But while it's not 0, these steps continue. They repeat themselves until the new r is 0. When the new r is 0, you exit the loop. What about if r is greater than 1? If r is greater than 1, you've done until the new r is 0, but r, which is supposed to be the remainder is still greater than 1. So if the remainder is still greater than 1, then this program is supposed to panic and tell you that the a that you input has no inverse. It has no inverse, so it will panic. That's why I said we are using mod p, where p is prime, because when you use p that is all prime, in some cases you get numbers that have no inverses, and therefore the program will not give you anything. Now, if t is less than 0, if t remember is the inverse. Remember, this is the inverse, and you're getting the inverse of a number mod m. So if you find that the inverse is 2 mod m and the m is 5, what I'm saying here is this t becomes t minus m. No, t plus m becomes t plus m. So supposing you had found t to be -2. -2 is less than 0. So what I'm saying, if t is less than 0, then what is t? T now becomes the t obtained plus m. This is what this Rust code means. This Rust code means that t is replaced by t plus m. Is replaced by t plus m. This is what it means. T plus equals m. That means the new t now is replaced by the original t plus m. That's what this code means. That's what it means. So what it means is that sometimes you'll be getting inverses which are negative. But when you do that, add m to them so that you have a positive value. That's what it means. And then you exit with the t. You exit with the t after adding m. Now, so this code has several parts, and one of the parts is the part that will be helping us to perform modular arithmetic inverses. The part that will be helping us to get inverses. Of course, we've seen where the inverses are coming in. For instance, where you have x minus r times x minus r over the denominator. And the denominator is a number whose inverse we want. So that inverse is then obtained by this code, this function here. So this is what that function is doing. Obtain inverse. Of course, then we have another function for Lagrange basis. Now, this one is now where we calculating our basis. That means we're calculating L0 of x, we're calculating L1 of x, calculating L2 of x, and so on. So again, it's mutable. You begin by initializing the numerator to 1 and the denominator to 1. Initialize that. They'll be changing. So then the formula comes in. The formula is if I is not equal to j, what does the numerator become? The numerator is the numerator. Be replaced by the numerator, of course, you were initialized. And you see, this is a loop. It means this process continues. This process continues until I becomes j. Then you exit. When it becomes j, you exit. But now what is happening? The numerator is the numerator times x minus xj. Of course, you'll be reducing it mod m. What about the denominator? It will be the denominator times xi minus xj, and so on. So this is a part that is calculating those the Lagrange basis. After calculating the basis, you know that we're supposed to multiply that by the respective y's, and then sum. So that's what we are doing here. The next function is now multiplying those Lagrange basis polynomial by the respective y values. Then summing the results. Then after summing the results, you reduce it mod p. Reduce the result mod p. What you come up with is the result after reducing it mod p. Then the main function prints the polynomial. But you see, the whole thing begins from here. The whole thing begins with this main function. You input the values, you input the mod, you input the values, you input the mod, and then when you run, it calls for the Lagrange interpolation function. The Lagrange interpolation function is this. So it has been called upon. This function has been called upon to produce the polynomial. This way it is. Let the polynomial. Then it calls on this function to produce the polynomial. For the points given, and the modulus given. Produce the polynomial for the points given and the modulus given. The points have been given here. Modulus have been given here. So it's now asking this, the function called Lagrange interpolation to give it the polynomial. So the Lagrange interpolation polynomial is here. It begins the process. But when it, at some point it discovers it can also not do some things, then it calls on, for instance, when it cannot find the inverse, it gets the inverse from above. And when it cannot find the Lagrange basis, it also gets the Lagrange basis from here. So you can see at this point, it's calling on the Lagrange basis. It's calling on the Lagrange basis to provide the basis with respect to I, where I could be 0, 1, 2. So that if you have L0 of X, you have L1 of X, you have L2 of X. So it reached here and discovered I don't have the L0 of X. Then it calls on the function responsible. The function responsible is the Lagrange basis. Lagrange basis. So it comes here. This is this function, Lagrange basis. So Lagrange basis has to provide that. So that is how the process begins from the main function, goes up to above, and so on. Let me share the code so that you can see how it runs. Okay, this is the code. This is the code. My main function is here. So I will input these values. I want it to give me the polynomial. Oh, this is a different code, but I also have it there. But what does this one do? This one is printing for me the points of when X is 0. These are different polynomial that are function that I wanted to look at next. But since it's the one I've opened, just explain what it's doing. So you give it the points, then it will give you the value of Y when X is 0. Then it gives the value of Y when X is 1. Gives the value of Y when X is 2. Gives the value of Y when X is 3, and so on. What are these? What are these value? The ones are multiplying by P. 0 is 0, 1, 2, 3. These are the values mod 5. Mod 5. Mod 5, you know that we have 0, 1, 2, 3, 4. So it then gives you the corresponding values for all those corresponding Y values. You can even increase this to mod 13, and you will see that it will then give you the corresponding values when X is 1, when X is 2, when X is 3, up to when X is 12. Because we are doing it mod 13. Yes, mod 13. We are doing it mod 13. And you see, it has given you, it tells you that this graph, it will be passing through 0.04, X and Y value, that is 0.14, it will pass through 0.23, it will pass through 0.31, pass through 0.411, and so on. So it gives you the values of Y corresponding to some values of X, mod 13. Because mod 13, we are talking of 0 up to 12. Okay, let me share the one that I wanted to share earlier. The name that I gave these polynomials. The name that I gave these polynomials almost, did I stop sharing really? I did not. I gave them almost similar names. That's why I may find myself sharing the same thing several times. Let me see whether it's. This is the same one. This is the same one. So what is the name of this one? Will it be this? Just a minute. Let me just get the correct name here. Get the correct name. Of this Lagrange finite field. Oh yes, I think it's this. Okay, let me see. Yes, it's this one. Now, I had asked it to give me the polynomial for these points. The point 10, x is 10, y is 14, x is -12, y is 14, x is 12, y is 13. Then when I ask it to give me the polynomial, it tells me it is 6x squared plus 12x, then plus 8, that is 1, 8, 1. That is 8 times 1. So that's a constant term. Now I change these points. You see, initially this was 0. This is 4. Let me just, so the initial polynomial, I was trying for several polynomials just to see that I get the same result before I say it's the right code. So this was my initial, and this is mod 5. If I make it mod 5 again, you get a different polynomial. So let me run this. So it tells me that it's 2x squared plus 3x, and then plus 4. The polynomial that will come out of these points, mod P, mod 5. Thank you. That is what I wanted to share today. But of course, we have explanation for the code. Explanation for the code is down here. And I've given an example of how it works. For instance, to get inverse, given an example here. Step-by-step example. Beginning from initial values, where you initialize, and then how it moves, calculate the temporal P, temporal T, new T, and so on up to how it gets the inverse, then how the code works to do the Lagrange basis, and so on. So when you get the notes and then the video, you can follow. Thank you. Unless there's any question. Is there any question on this? Okay, if there's no question, then we stop there. Alex, is there any announcement?
No announcement today. Thank you, everyone. Thank you. I think we meet, apart from the issue of us meeting on Tuesdays instead of Mondays. So the next class is on Tuesday, 8 p.m. Then we'll meet on Thursday, then on Friday. So instead of Mondays, we've moved the class to Friday. So I'll share a timetable in the groups.
Thank you.